This is an overview today of how to draw pictures of molecules. The instruction today goes back to the quizzes we took last week about adding valence electrons, and today we're going to try and use that skill and some other skills to draw pictures of what molecules might look like. So when you're drawing a picture of a molecule, the first thing you want to do is add the valence electrons. So I'm going to say rules for drawing dot diagrams. Sometimes these are called Lewis structures, so I'm going to call them Lewis dot diagrams. And really what those are is pictures of molecules. Okay, rule number one, add the valence electrons. Okay, so when you add the valence electrons, if you look at, say, PF5 right over here on the left side, PF5 right here, we add the valence electrons. We would look at P over on the periodic table. Remember, it's in the fifth column, so that's 5 valence electrons. So the P has 5 valence electrons. Let's go back up here, periodic table, come back here. It has 5. I do that up in the corner here. And the other element over here is F, and F is with 7 valence electrons. So 7, but since there are 5 atoms of the fluorine, then I have to multiply that 7 by 5. So 5 plus 35 is 40. So there would be 40 valence electrons in PF5. If we wanted to add the valence electrons in NF3, it would be 5. This is NF3 now. So we have 5 plus, and then boron in F3, 5 for nitrogen, so the nitrogen's right here. And then fluorine is 7, so because it's over here, so 7 times 3 would be 21. So 7 times 3 is 21. So you'd end up with 26 valence electrons. So that's what I mean when I say add the valence electrons. Step number 2 would be to draw a skeleton structure. And a skeleton structure, what that means is, like if we did, I'm going to do the NF3 right over here. We'll draw it first. So we'll do NF3. We already said that there are 26 valence electrons. 5 plus 7 times 3 is 26 valence electrons. So if you draw the skeleton structure, you'd put an N in the middle, and then you'd put the F's around the N, like that. So you're connecting them with a bond, and that bond represents a shared pair of electrons. So when I talk about bonds, a bond is a shared pair of electrons. All right, so the second rule is draw a skeleton structure, and I'm going to put some rules about what goes in the middle. In the middle, okay, things to consider. What goes in the middle is the element closest to the middle of the periodic table. So if you look at N and F, you see how N is closer to the middle. Okay, another thing to think about, and so, sometimes you have to choose your best option from options that aren't always perfect. So you would say the least electronegative So you remember electronegativity increases as you move up and to the right, and N would be less than F, so the less electronegative goes in the middle. Like we have down here. Or the element with the most open spots. So if you look at N, it's got 5 valence electrons, so it would have 3 open spots, but F has 7, so it only has 1 open spot. The one with the most open spots goes in the middle. Okay, now rule number 3 for drawing dot diagrams is subtract 2 electrons for each bond. So what that means is, over here in our picture, I have 2, 4, 6 electrons in the picture. So if I take my 26 valence electrons and subtract 2 electrons per bond, there's 1, 2, 3 bonds, so 2 per is 6. 3 times 2. That would give me 20 left over. Okay, after you do that, the next thing you do is put in the remaining electrons per the octet rule. Now you'll remember when we were talking about valence electrons, we said that atoms tend to gain or lose in order to get to 8 in their outer shell. So everything wants 8 in the outer shell, with a couple of exceptions I'll go over in a minute. But in this case, there aren't any exceptions. So we need 8 electrons in the outer shell of nitrogen, fluorine, and all the fluorines. And I have 20 electrons to put in order to attain that. So here we go. The fluorine already has 2 in its outer shell because that pair of electrons is 2. So if we put in 6 more, that would give us 8 in the outer shell of fluorine. See, 1, 2, 3, 4, 5, 6, and that counts as 2. It's a pair of electrons. Same thing down here, 1, 2, 3, 4, 5, 6, and that counts, this one counts as 2, so this fluorine now has 8 in its outer shell. 1, 2, 3, 4, 5, 6, and these 2 make 8. The same thing will happen over here, 1, 2, 3, 4, 5, 6, and then these 2 make 8. So now we have used 6 dots here. Okay, so I'm going to write over here 20 dots to put in, just to remind you what we're doing. So I've put in 1, 2, 3, 4, 5, 6, and 6 more makes 12, and 6 more makes 18. So I've got 18 of my 20. I have 2 more left that I need to put in. I'm going to put them on the nitrogen because the nitrogen already had 2, 4, 6, and then 2 more makes 8. Now remember, this shared pair of electrons, they count as 2 electrons for each of the atoms. Because they're sharing them, it's kind of like if you have one car but you share it with a sibling, then you're sharing a car and you both have one car but you don't completely own it. That's the way these bonds are. This fluorine and this nitrogen both own these electrons, this pair of electrons, but neither one of them owns them completely. Turns out the fluorine owns them more because of the attraction that they have compared to nitrogen. Fluorine is more electronegative. Okay, now here's a couple of notes. Some atoms do not obey the octet rule. They are: hydrogen only gets 2 electrons total, period. You can never have more than 2. Boron only gets 6 electrons max. Beryllium all right, so other than that, you're going to shoot for 8 around everything. Sometimes you have to put more than 8, and we'll get to that in a minute. All right, so now rule number 5. Let's do another dot diagram. So that's the dot diagram for NF3. Rule number 5. Let's look at an example. So let's suppose we try to do CO. That's down here in this point. Okay, so actually let's do NO3. I'll do NO3 first. So NO3. Okay, so you look at N on the periodic table, it's right here. It's got 5 valence electrons. You look at O, it's got 6, because it's in the 6th column over there. And the other thing that's interesting about this has a little minus sign. So that means overall there's 1 extra electron. So if I'm going to add up the valence electrons following my rules, add the valence electrons for CO. Then I'm going to have for NO3, I'm sorry, for NO3 we're going to add the valence electrons. I have N has 5, O has 6, so 5, 6, but there's 3 of them, times 3. And then that little minus sign that's in the picture over here, that minus sign means that there's one extra one overall. So that's 1. So my total would be 5 plus 18, that's 18 plus 1 is 24 valence electrons. So then you draw your picture. You have the N in the middle because it's closest to the middle of the periodic table because it's the least electronegative and it also has the most open spots. So N, O, 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 like that. Notice I'm kind of drawing these electrons away from each other, this pair here, away from that pair, away from that pair. And I sort of did that up here too. The idea is that the electrons repel each other. They want to get as far away from each other as they can because they have a negative charge. All right, so I had 24. Follow my rules. Second rule, subtract 2 electrons per bond. Or we do a skeleton structure, I did that. And then subtract 2 electrons per bond. So I'm going to take away 6. That gives me 18 dots to put in. All right, so the 18 dots would go 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That makes 8 around the oxygen. You see 2, 4, 6 plus these 2 make 8. 2, 4, 6, these 2 make 8. 2, 4, 6, and these 2 make 8. So there are 18 dots to put in, and I still have a problem because I'm out of dots, but I still need 2 more dots that I don't have, and they need to go around the nitrogen. So what do I do with that problem right there? Well, what you do is you add it again, or you start again, but this time you add a double bond. Now I'm going to say that I was 2 electrons short. The reason I'm 2 short is because I need 2 more to go here. Now if you put a double bond in, you take 24 minus 1, 2, 3, 4 pairs now, so minus 8, 2 per pair. And that gives us 16 dots to put in. So 1, 2, 3, 4, 5, 6, and that oxygen's happy. 1, 2, 3, 4, 5, 6, and that oxygen's happy. So that leaves us 4 more to put in. So I can put 1, 2, 3, 4. Would that satisfy this oxygen? And the answer to that is yes, because you have 2, 4, and then these 2 and these 2 make 8. And around the nitrogen, 2, 4, 6, 8. So by sharing a pair of electrons, we can make everything happy. So rule number 5 over here is if you are 2 electrons short, add a double bond in the skeleton structure and start over. Okay, so add a double bond in the skeleton and start over. Now, that brings us to rule number 6. Sometimes you'll be two pairs short or 4 electrons short. So to run into that, let's take a look at CS2 up here. So CS2, move this to the left a little bit. All right, so CS2. So you go to your periodic table, you find C. It's right here, it's got 4 valence electrons. Sulfur's got 6, so I'd have 4 plus 6 times 2. So we're looking at 16 valence electrons. Set up your skeleton structure. I'm setting up again so that the electrons are as far apart from each other as they possibly can be. You take away 2 per bond, so I take away 4, gives me 12 dots to put in. So if I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, that all looks nice until I realize that there's an empty spot there and an empty spot there because the carbon needs to have 8. And right now it only has 1, 2, 3, 4. There needs 8. So I really am 4 electrons short. I don't have enough. I need 4 more. 4 electrons too few. Short means too few. So the 5th rule is, excuse me, the 6th rule is, if you are 4 electrons short, add a triple bond or 2 double bonds and start over. Now, a trick is to maintain symmetry if possible, which means keep it even, keep everything looking symmetrical. Oops. All right, so here's what that means. We draw our dot diagram over here. We're going to put our, in this case, if I had, which is more symmetrical, putting a dot diagram like that or this. See, this one's more evenly spaced around and that one's not. So don't do that, do this. So now we still have 16 to work with, but now instead of subtracting 4, we're going to subtract 1, 2, 3, got 4 pairs, so that's 8. So 16 minus 8 is 8 dots. Put them in here. There's 4. Does that make 8 electrons around the sulfur? Yes, because there's 1, 2, 3, 4, 5, 6, 7, 8. And then if you put 4 over here, 3, 4, 5, 6, 7, 8. So I have 8 dots around the sulfur, 8 dots around the carbon, and 8 dots around this sulfur. And the 8 around the carbon are right here, 2, 4, 6, 8. So that's our dot diagram for CS2. All right, the last one, rule number 7. It'll look like this. If you have extra electrons, too many, add the extra electrons to the center atom. All right, so let's look at one that might show us that. SCl6 would be a good example. Would be fine, we'll look at it. And so it looks SCl6. It goes like this. SCl6, we have sulfur has 6 valence electrons, chlorine has 7, so we've got 6 plus 7 times 6 because there's 6 atoms. 7 times 6 is 42, plus 6 is 48 electrons. Then you draw your skeleton structure. You want to keep the skeleton structure as symmetrical as possible, so you think about things radiating out from a center. So you see in this case I've got too many electrons around the center, but sometimes that happens. So you put your CLs in, you got 48, so you take away 2, 4, 6, 8, 10, 12. That gives us 36 dots. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22, 3 to 4, 5 to 6, 7 to 8, 9, 30, 2 to 3 to 4 to 5 to 6. So everything's happy with 8 electrons around it except for the sulfur, which has too many. But that's okay because they're around the center atom. Okay, so that's your dot diagram for SCl6. And I'm just sorry I had that off screen, so I'll run through that again real quick. You had 48 electrons. There were 12 in our dot diagram. 1, 2, 3, 4, 5, 6. So 6 times 2 is 12. Gave me 36 dots. I put 6 here, 6, and 6, and 6, and 6, and 6, which makes 36. So all the chlorines are happy with 2, 4, 6, 8 electrons around them. The sulfur has too many electrons, but they're around the center atom, so that's okay. So there we go. Now let's take a look at BRF5. That's another one over here, BRF5. So BRF5 would look like this, BRF5. Bromine and fluorine both have 7 electrons in their outer shell, but bromine is the least electronegative, so it'll go in the center when we draw our structure. So we'd have Br like this, 1, 2, 3, 4, 5, F, F, F. Okay, so 7 times 5 is 35 and 7 is 42. Minus 2, 4, 6, 8, 10. We have 10 electrons already in the picture, so that leaves us 32 dots to put in. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. There I've put in 30 dots, 6 times 5. But I still have 2 more. And where do the extra ones go? So extra electrons go around the center. So I put the other 2 electrons here, and that would be the dot diagram for BRF5. There. All right, now if you go on this page I put on here for practice, the answers are down here, so let's talk about the answers. Here was BRF5. So there are 42 electrons. There, you can ignore this OH and square pyramidal. We'll get into that tomorrow. So the next video will deal with shapes. But that's the picture. Notice that what I have put in as bonds because I think it's less confusing to do it that way. So see that pair of electrons I'm pointing to, that's this pair of electrons here. They put in as a pair of electrons. If there was a double bond, then like the one we did with CS2, see how you have 2 pairs in between. So if you want to see, you could draw a line from there to there and a line from there to there, and that's the 2 bonds that I have in the CS2 that I drew over here. See those 2, 4, here they are, 2, 4. All right, so those are your answers. You'll be able to check your work by looking at that page. All right, 40 for PF5. I didn't do PF5. Let's see, I did SCl6. SCl6 right here. So there's 48. And you see how there's all single bonds in between the sulfurs and the chlorines. All right, so practice on these a little bit, and there's a quiz posted, and tomorrow I'll give you more instructions. Remember, we're trying to figure out why was it that I was able to put 21 drops of water on a penny, but only about 14 drops of alcohol. So we're looking at about what characteristics of molecules make them attract each other more or less. All right, that's a little bit longer than my normal video, so we'll end it there.